For all these algorithms that we will use from now, we will use so-called network flows. So in this part, I will introduce to you ST flows and minimum cost flows. If you already know those, you can skip this part and immediately go to part 4. But if this is new for you or you want a refresher, then stay with me. A flow network might look like this. We have here the largest rivers from the Iberian Peninsula. And if we look at this, we always have some sources where the water comes from, and we have some sinks where the water flows to, which is usually the ocean. We can model this flow of water by a graph. So we can create a flow network that consists of a graph G, a set of vertices S, a set of vertices T, and a function U. The graph is a directed graph, and the vertices we have are on the one hand the sources where the water comes from. This is also our set S. Then we have the sinks where the water flows to. This is also our set T. And then we have additional vertices on these crossing points where two rivers meet. And since it's directed, all these are directed from the sources to the sinks, so in the direction of the water flow. And this function U, this gives us the edge capacity. So that tells us for every river how much water can flow through this. In this example, we can put some numbers here. Now this means that this river can have at most 3 flow, this can have at most 1, this can have at most 5, this at most 7, and so on. Now we want to find a valid flow here. And a valid ST flow is a function that assigns to each of these edges in our graph a flow. So it tells each of these edges how much water flows through you. And the condition for this is, of course, it cannot be negative and it cannot be more than the capacity. So in this example, we can put some numbers here. As long as they are between 0 and the capacity, everything is fine. I just chose to use the capacity for all of them. But this is not all. There is a second condition. Because if we look at this vertex here, we have a flow of 1 coming in, we have a flow of 3 coming in from here, but then a flow of 5 leaves. That means that this must have produced some water, but that usually doesn't happen when two rivers meet. So for this to be realistic, when we have two rivers that meet, what goes out should be exactly as much as what came in. So that means for every vertex that is neither a source nor a sink, so all these white vertices, what goes out, so the sum of all the flows of directed edges that leave this vertex, minus what comes in, so the sum of all the flows of edges that enter this vertex, must be exactly 0. So this here we have to fix. If we have a 1 here and a 3 here, then this must be a 4. There are a few more. For example, here we have a 2 and a 1. That means this must be a 3. And this was fine before, but now we made this as 3, so this continues. We also have to make this a 6. It can also be the other way around, like here. We have 2 flows of 5, but this only has a capacity of 7, so this does not work. We cannot put a flow of 10 through this edge. That means we have to change these. And there are a few ways we can do that. For example, we can make it 5-2 or 2-5 or 4-3. We might also make both 3.5, but we will focus on the integers numbers here. Now it's very easy to find a valid ST flow. We can just put a 0 everywhere and we have these conditions. But that's usually not something that we want. Usually we want to maximize the flow that we get. And a maximum ST flow for us is an XT flow where the sum of all these flows at the sources are maximized. So we take all the edges that leave the sources and we sum up what is the flow here, and that gives us the total flow of the network. Alternatively, you could also look at this flow that you get at the sinks, but if everything works out here, that should be exactly the same number. Most of the time in flow networks, we don't have many sources and many sinks, but we only have a single source and a single sink. And this is again an ST flow, but now it's a small s and a small t. So instead of a set of sources, we use a single source S, and we use a single sink T instead of a set of sinks. And then the conditions here are almost the same. We only have to change this slightly. This now all the vertices except S and T. And a maximum ST flow is again ST flow, where the sum of the flows is maximized, but now we only have to look at all the edges that leave our single source S. And restricting to a single source and a single sink, this is not a problem. We can easily take this network with many sources and sinks and transform it. For that, we simply add a super source here and connect it to all the sources that we have. And then we add a super sink here and get incoming edges from all the sinks that we had. And if we make the capacity for all those additional edges infinity, then if we have a flow in this ST network, then we also get a valid flow in the input network and the other way around. It's completely equivalent. So as long as we can solve this case here with a single source and a single sink, we can also solve the case with many sources and many sinks. For this type of flow networks, there are many different algorithms. I want to show you briefly two of those, but for that we need the definition of a residual network. So let's have a look at a smaller example here. We have a flow network, we've already assigned some flows. Then we create the residual network that depends on this flow as follows. We take exactly the same vertex set, and for every edge here, we have a directed edge in the same direction as long as it is not completely full here. So as long as the flow is smaller than the capacity. This is the case for almost all of them except this one and this one here. But then we also add edges in the other direction as long as there is some flow here. Well, this is the case for all except this one here. I will color them red now. For these we will use different capacities. For the black edges, the capacity will be exactly the difference between the capacity here and the flow here. So this gets an 8, this gets a 9, and so on. And for the red edges, we take its capacity exactly the flow that we have here. So this is also an 8, but this is a 4, this is a 12, this here is a 3, and so on. Now what does this tell us? This basically tells us how much can we change the flow on these edges. So on this edge here, there's 8 capacity left. So we can add 8 in this direction, but there's also 8 here, so we can also remove 8. For this edge, there's 6 capacity left, so in this direction we can add 6 flow, and we have 3 in it, so we could also remove 3. And now a path in this residual network will tell us how much we can change the flow of some of these edges and still get a valid ST flow. And these are the so-called flow increasing paths. So we go from S, we find a path here that can have some black and some red edges. And now if we look at this, we have an 8, a 4, an 11 and a 1. So we can change all those numbers, but we have to take the smallest on the path. So we can change this only by 1, can change this by 11, this by 4, this by 8, but because of our restrictions, that means the largest thing we can do here is change all of them by 1. So this is increased by 1, this gets decreased by 1 because this is a red edge, This gets increased and this gets increased. And now if we do that here, then we have a flow that's by 1 larger. Here you see we have 8 plus 4 is 12, and now we have 9 plus 4, that's 13. And with these flow increasing paths, we can solve the maximum ST flow problem. One algorithm I want to show you is the Ford-Fulkerson algorithm. That takes as input exactly our flow network, and what it does is it starts with a 0 flow at every edge, and then at every step it creates the residual network and finds some ST path in it. We take the smallest capacity on this path and we update the flow for every edge here. So for the black edges we add this, and for the red edges we remove this. And by iteratively doing this, we keep increasing the flow until at some point we get to the maximum solution. And this algorithm works in order of x star times n time, where x star is the maximum flow and this is the size of the maximum flow. Let's have a look at one small example. We have a graph here with 4 nodes. We have capacities 1000 here and 1 here. We create the residual network and we find some path here. Now we can increase the flow for everything on this path by 1 and we get this one. We create the new residual network. Now we have some red edges and again we find a path here. That means that for these two we increase the flow by 1 and for this we decrease it by 1. So we get this flow here. Now these edges have a 1 and you can see we have to repeat this whole thing 999 more times until we finally get to the best solution. And the best solution has a flow of 2000, so we need 2000 steps. For every step we need order of n time, so it takes a long time. But there is an improvement for this by Edmonds and Karp. And they say, instead of just choosing any path, they take the shortest path. And if we do that, then we can solve the problem order of m squared times. So number of vertices times edges squared. This can be more or can be less depending on this capacity function. Let's have a look at the same example. If we take the residual network here, we will not choose this path because this path at the top is shorter. And now we can increase both of them by 1000. Now we create the new residual network. Now these edges are both red because they are full. We find the shortest path, which goes down here, and we increase both of those by 1000. And what now? Now we're done. There is no ST path here anymore, and we can clearly see that this is a maximum ST flow because all the edges at S are completely full. So we're already done after 2 steps. These ST flows, they are quite special cases of flow networks. And we can generalize this to general flow networks. Here, in addition to a capacity, we also have a lower bound for every edge. So for every edge, we also have a minimum number that must be met. I just add a few of those. You can imagine the others are zeros. That of course changes this part here. Now this flow must not be between 0 and the capacity, but between the lower bound and the capacity. Also, we get rid of the sources and the sinks, and we replace it with a production and consumption function. And this basically tells us for every vertex how much water do we produce or how much water do we consume at this point. So instead of the difference between what comes in and goes out to be 0, it must be exactly this number that we get from this function. In total, all these productions and consumptions must sum up to a 0, otherwise it's impossible to get a valid flow. Now here we can already ask the questions, can we find a valid flow? Which is much harder than before because we cannot just choose everything to a 0. But we can generalize this even more. We can also say that some of these rivers are more expensive than others. So we can also assign a cost function to every edge. And then for the cost of the flow, we sum up the cost of every edge multiplied with its flow. If you put this to a 1 everywhere, then the cost is just the total flow that you have in the network. But maybe some of those are more expensive than others, and this gives you even more freedom. And now the question is not to find a maximum flow, but a minimum cost flow. So we want to find some valid flow where this cost function is minimized. And this is a very old problem, and there are many different algorithms that solve this with different running times. There are two that I want to point out to you. The first is the, as far as I could find, fastest algorithm that solves the general version of this by Orlin 1991 that takes n squared log squared n plus m squared log n time. For a special case that we will see in the next part, there's an algorithm by Cornelsen and Karrenbauer. They say if the network is planar, it has bounded costs, and the faces have bounded size, then we can even solve this in order of n to the 3/2 time, which is much faster than this, because already this term dominates it. And in the next part, we will model our band minimization problems with flows.